Hello, and welcome to our lesson on applying what we've learnt with one equation to multiple simultaneous equations. This will build on your existing understanding and elevate your problem-solving abilities. In this lesson, we'll cover the following key points. First, we'll establish how the equations of lines can reflect whether they are parallel. Then, we'll delve into understanding the specific characteristics these equations must have for two lines to be parallel. Finally, we will apply this new knowledge to various scenarios, reinforcing our understanding and showcasing the utility of this concept in solving problems. In our previous lessons, we've laid a strong foundation by discussing parallel lines and understanding how they never meet. With this solid base, we can now introduce the notion of representing parallel lines through equations. This technique is highly useful in algebra and geometry, as it allows us to precisely describe and analyze the behavior of lines in a coordinate plane. Let's dive into the main concept of our lesson on representing parallel lines with equations. In a geometric sense, parallel lines are always equidistant and never meet, no matter how far they are extended. In algebra, we describe lines using equations, normally in the form y equals mx plus c, where m is the gradient or slope of the line and c is the y-intercept. Now let's connect this information. We know that parallel lines have the same direction. Secondly, we know that the gradient m tells us the direction of a line. This means that parallel lines must have the same gradient. Vice versa, if two lines have the same gradient, we can conclude that they are parallel. Let's take a look at some examples to solidify this concept. Consider the equations y equals 4x plus 1, y equals 2x, and 2y minus 4x equals 8. First, convert any equations that are not in the y equals to mx plus c form. For example, the third equation can be rearranged to y equals to 2x plus 4 by dividing everything through by 2 and adding 2x. Now we have the equations in the form of y equals mx plus c, so let's look at their gradients. For our first equation, m equals to 4. In our second equation, the gradient m is 2. For our third equation, the gradient is also 2. From these gradients, we can see that the equations y equals 2x and y equals 2x plus 4 have the same gradient, where m equals to 2, indicating that these two lines are parallel. The line y equals 4x plus 1 has a different gradient as m equals 4, so it is not parallel to the others. By using these fundamental principles, we can determine the relationship between different lines just by inspecting their gradients from their equations. This approach saves time and effort compared to graphing each line individually. In the next step, we'll apply this knowledge to various scenarios to reinforce our understanding. Are the lines y equals minus x plus 7 and y equals 3x plus 1 parallel? To determine if these lines are parallel, we need to look at the slopes of each line. Recall that in the equation of a line in the form y equals mx plus c, the coefficient m represents the slope. For the first equation, the slope m is minus 1. For the second equation, the slope m is 3. These lines have different slopes, minus 1 and 3, so they are not parallel. Lines with different slopes will eventually intersect. Are the lines 2x plus 3 equals 6 and 6x plus 9y equals minus 9 parallel? Sometimes equations are given in the form asx plus by equals c. This is known as standard form. To compare the slopes, we need to convert these equations to the slope-intercept form, y equals mx plus c. For 2x plus 3y equals 6, we need to subtract 2x from both sides and then divide by 3. Doing this, we get y equals minus 2/3 x plus 2. For our second equation, we subtract 6x from both sides and divide by 9. After simplifying, we get y equals minus 2/3 x minus 1. Now both equations are in the form y equals mx plus c. The slope of the first line is minus 2/3. The slope of the second line is also minus 2/3. Since both lines have the same slope of minus 2/3, they are parallel. Let's look at a real-world problem. The following lines represent the boundaries of two roads. Are they parallel? Our roads are y equals 1/2x plus 5 and y equals 1/2x minus 3. For our first road, the gradient is 1/2. For our second road, the gradient is also 1/2. Since both slopes are equal, the roads represented by these lines are parallel. By working through these examples, you can see that identifying parallel lines boils down to checking that their slopes are identical. This method is straightforward and saves time, allowing us to focus on solving more complex problems efficiently. Keep practicing with different equations to reinforce your understanding. Before we conclude our lesson, let's consider the historical background of parallel lines. Did you know that the concept of parallel lines was explored by the ancient Greek mathematician Euclid in his work Elements? Euclid's Elements has influenced geometry for over 2 millennia. In this foundational text, he meticulously defined parallel lines as lines in the same plane that never meet, no matter how far they are extended. His work laid the groundwork for much of modern geometry, and the principles he established are still taught in schools today. In today's lesson, we explored how to represent parallel lines using equations. We began by recalling that parallel lines never intersect and have the same direction. In algebraic terms, this translates to having the same gradient. We discussed linear equations in the form y equals mx plus c, where m represents the gradient. By understanding that parallel lines share the same gradient, we can quickly determine if lines are parallel just by comparing their m values. We also practiced converting equations into the form y equals mx plus c to identify their gradients. Through examples, we saw that lines with identical gradients are parallel, while those with different gradients are not. This method allows us to analyze relationships between lines efficiently without needing to graph them. This knowledge is crucial for solving more complex problems in both algebra and geometry. Watch the rest of the GCSE Maths course at Sophos Education.